Okay, so the mic. Sorry, I had the mic off. Okay, so so the mic is on, and we're getting started. So the idea today is to sort of go over the solution to the general linear model problem, and then hopefully try to make it somewhat clearer with a with a geometric diagram. I'm not going over the details of how we get the solution, but I'll just draw it up so you can just get some idea of how how these things work or how people think about it. So if we start again with the basic equation. So the basic equation for the general linear model was there's a vector of data, and that is equal to this matrix, which is the convolution sort of turned into a matrix. So this thing is convolving our experimental design with our hemodynamic response function vector. That's the unknown. And then there's also this nuisance vector matrix, which are things that actually appear in the signal. They're real things in the signal, but they're ones that we don't care about. And then there's a set of, and that matrix is multiplying a vector of weights of each of those nuisance nuisance vectors. Like so, the nuisance could be something like a linear trend that goes with time, and then this thing will just be how much weight that linear trend has in explaining part of the data, and then finally the noise vector. So then the plan is we need to solve this. So we need to sort of figure out the h and the b. So how do we solve for the h? So the idea is brand new one. So we first assume white noise. So this thing is called, the thing that I'm drawing up here, this is from the Tom Liu paper in the reading. So this is called the maximum likelihood estimate. So maximum likelihood estimate. So the first thing is we make some assumption about what the noise is like. So we're making an assumption about what that noise is like. That helps us, that sort of adds a little information into this equation to help us solve for this unknown. So if we then do the solution, which I won't explain, we get this h hat vector. So this is our best estimate of what the real hemodynamic response function is. So this is, let's just annotate these quick. So here's the experiment, and this guy is HDR, and this guy is nuisance, and these are weights, and this is noise, and this is data. Experimental. Okay, so if we solve that guy, solve for the h. So here's our horrible matrix equation. So the interesting thing about writing out matrix equations is that you can sort of deal with them like regular equations, even though there's a whole bunch embedded. So this is the experimental design matrix, and that might be a matrix that's like 400 by say 50 or something like that. So it's a giant matrix of numbers, 400 this way and 50 all filled in with numbers, but we're just sort of compressing it all the way down to just a single variable. And we can sort of think about it. We can think about operations on these matrices just like more simple equations that we're more used to dealing with of just single variables. So here's the solution. It's the transpose of that matrix. That's kind of like where you kind of mirror the matrix, or sort of rotate swap the rows and columns. And then there's a projection matrix here. Well, this is the S projection matrix, and then times the experimental design matrix again, and then that whole thing inverted. So that's like 1 over it. You can think of it basically when you do a matrix inverse, it's kind of like just doing 1 over a matrix basically, and then multiplied by the transpose of the matrix again, and then yet a different matrix here. This one is the perpendicular projection matrix, and then finally times the data. So this is hemodynamic response function vector solution equals matrix times matrix times matrix. Invert that whole thing after you've multiplied those matrices, multiply by 2 more matrices, multiply by the data. So you stick the data in here and you get the hemodynamic response function out. And there was, we didn't define a couple of the things in there. So where this guy is equal to a whole nother set of matrices. So this is I minus the S matrix times the S matrix transpose times S matrix. If you want to square a matrix like x squared, typically what you'll do is you'll transpose the first element of the matrix and then multiply it, and that will give you a square of a matrix. And then the inverse of that guy times the transpose again. Okay, so it's just like hundreds of thousands of numbers, but we've compressed it all down to just a couple letters. And there's in the notes I have another way of rewriting this a little more simply, where you try to regress out part of the nuisance vectors first. But that's the solution. So this guy is the solution to this is our deconvolution basically. So this is solution, which is our deconvolution. So we're instead of convolving, what we're doing is we're solving for the unknown hemodynamic response function. So that's our solution. And then finally, we want to get the significance out of that. And so the significance, this is, is our F ratio, variance ratio, that will tell us, after we've done this solution, how significant is that hemodynamic response function solution. And so this one now, so there's our F ratio, so that's just a number. So we just get like one number out of first the degrees of freedom. So here's the degrees of freedom. So this guy was, this guy was time points. This guy was, steps in HDR. How many hemodynamic response function time points, like say 5 or 10 seconds worth, and this was the weights for our nuisance variables. And that whole thing divided by k, and then it's multiplied by the things that I'm going to make a geometric diagram of. And so that was the signal. So the signal was the transpose of our data times yet another matrix, which we'll describe, and another matrix over here times y. So that was our signal divided by our noise. And our noise is the data transposed. I stands for the identity matrix. That would be like a giant matrix with just ones like here and zeros everywhere else. I'll explain what that means. So then here's that same matrix again times y. Okay, so that's basically our signal over noise. So when you look at these equations like this, you can do operations like you would do in regular algebra. So like when you see this, this is a matrix minus a matrix times a vector. So you could write that out as, the identity matrix times a vector. That won't do anything to the vector, minus this matrix operating on the vector. So, you can take that and just distribute that equation like you would do if it was just a single variable, even though it's 20,000 numbers. So so I'm not giving you enough information to sort of really understand how to do this, but it's just a sort of introduction that you can end up dealing with these matrices as if they were just simple equations with some slight differences, like you have to do when you're squaring something. You have to sort of transpose the first element when you're squaring it. There's a few slightly different operations, but then you can sort of deal with it more or less like you were just dealing with regular numbers. So this is just to inspire you to take the matrix algebra course that I never quite finished. Okay, so this is the significance. So this is the solution. This tells us, this actually gives us the hemodynamic response function, and then this guy tells us how significant it is. So what does this significance mean, and why is it sort of get a little more complicated? And so for this, we want to consider the problem that we've got sort of the experimental design and then the nuisance part. But the problem is those might be partly correlated with each other. And so this is a typical problem. And so the problem is the nuisance functions maybe, or nuisance, we'll say nuisance space, because remember we're thinking of this as these time courses forming a space. So like a point in the space is a time course. So the nuisance space may be not orthogonal, meaning equals uncorrelated. So it might be not uncorrelated with experimental design. And so I'll give a simple example so you can see geometrically what this is. So experimental design space. So how can sort of spaces be, orthogonal or not orthogonal? So remember, the way we're thinking of this is we're thinking of, here's our X matrix. Our X matrix, it's rectangular this way. And here's the columns of numbers in the X matrix. So the columns of numbers in the X matrix are the basis vectors, sort of like, the X, like the X direction or the Y direction or the Z direction. And so we have more basis vectors like than X, Y, and Z, more dimensions. And then each vector, contains, sorry, I said it wrong. So each vector contains a series of numbers, and those are like X, Y, Z, and then, the fourth dimension, the fifth dimension, the sixth dimension, seventh dimension. So each of those vectors is basically pointing in some direction. So like, if you just do, say, X, Y, Z, like what is the Y vector? Well, the Y vector is 0 for X, 1 for Y, 0 for Z. So that's what these vectors are like. So they're like, except they've got, instead of 3 dimensions, they have 400 dimensions, because they have as many dimensions as time points. So this is time going in this direction. So, and then these guys, so each one of these guys are the basis vectors. Kind of like this, like the y-axis is a basis vector. And then we have the same thing, for the S matrix. The S matrix isn't as big, but we have the same thing going on for the S matrix. And so what is our problem? So our problem is, what if these guys are partly correlated with each other? So let's just give a simple example of how that might occur. So if we have a simple experimental design that's just off, on, off, on. So that's a simple experimental design like that. So this is like our block design. So that's 0 and 1. So we just have we just have 2 offs and 2 ons. Now let's take a nuisance, a typical nuisance. So a typical nuisance might be linear trend, nuisance linear trend. So that's a real thing in the signal, but it's one that we don't care about. So let's take a 0 mean linear trend. So it goes like this. Okay, so that's a nuisance variable. That's something that's part of the S. It's a real thing that we're going to allow to add in and explain some of the data. But the problem is, what's the problem? Well, the problem is it's not uncorrelated. It's not orthogonal to this experimental design. Experimental design. And so what does orthogonal mean? Well, orthogonal, or what does uncorrelated mean? Uncorrelated means the dot product should be 0. So if you have two vectors, if they're perpendicular to each other, the dot product will be 0. If they're parallel to each other, the dot product is big. So so we have to calculate the dot product, and how do we do that? We just multiply all these guys times each other, and then sum them up. And so let's just sort of graphically do the dot product. So if you just do the dot product, here's the dot product, you're going to get something that you're multiplying by 0 here. So up to here it's going to be 0. And then what's going to happen is you're going to be multiplying by a negative number like that. And then you're multiplying by 0 again, over here. And so then now it's 0. And then you're multiplying by a big number. So you'll get something like that. So then to calculate the dot product, we just add those all up. And so, when you do this, sum not equal 0. So when you look at this, what's going on? It's, you had like an off and an on, and then an off and an on, and it's kind of more on-y. It's more on-y toward the right. But the linear trend is like that also. It's bigger toward the right. So what that means is that the linear trend has some signal in it that looks like the block design. Looks like a response from the block design. So that's a problem. So that means that if we, for instance, just regress out the linear trend, we could be taking some signal with us. So for instance, I could just say, let's just remove the linear trend. So I remove the linear trend, but that's actually going to remove part of the signal also, because the signal is, it seems a little more weighted toward the right. So that's the kind of problem you can have when these two sort of spaces of, so what are these things? They're spaces of possible time courses. That's the meaning of that's the way you should think of the experimental design matrix. It defines experimental defined matrix, just the matrix of the experimental design where the zeros and ones of your stimulus are, defines a set of possible time courses, possible data time courses. And the nuisance matrix does the same thing. So the nuisance matrix with these linear trends, or maybe polynomial sort of like low frequency changes that are like movement artifact, that defines another space that's of possible time courses. It doesn't say which one, it just says like here's a space, and there's like I can explain any time courses that exist in this space. So that's the kind of, it's a very abstract way of thinking about it, but it's useful to sort of eventually go there. And like I said, I'm not giving you enough of the math between how we do these solutions, but I just want to sort of just go over really the conceptual approach to these things. So now let's go back to here, which is a way of solving this problem. So this, this solves this problem. So how does it solve this problem? So for this, we want to sort of make a geometrical picture of this. So a geometrical picture of, what is this? So if you're like me, like a little 2D picture. So remember, since we're primates and we have like a visual system, it can do, 2 and 3D. The basic input to the visual system is actually 2D because, it just has a map of the retina. So the retina is a two-dimensional thing, but, we've learned how to take those two-dimensional inputs that come into our retina and infer like what an actual three-dimensional object was. So we've only got 3 dimensions to work with, unfortunately. So we're going to have to make this picture just a 3-dimensional picture. But, 3 is okay. It's more than 2. Okay, so we start off. So we start off with a big space here. So this is our space. And what is this space? This space is the XS space. So this guy is. So this is the space of all the kinds of time courses that can be explained by the experimental design matrix, and also the time courses that can be explained by the nuisance variable matrix. One last thing I forgot to mention. So which is another thing that this equation solves. So let me just quickly go over that. So, sorry, I should have put this before. So if the experimental design matrix is uncorrelated, the time courses in there are uncorrelated with the time courses in the, if the nuisance time courses are in fact uncorrelated, meaning that they're at a right angle to the experimental design time courses, and we've got some data, so here's some data that includes both. It includes both, there's that sort of, so here we're just doing it in 2 dimensions. We've got experimental design in this direction, nuisance in this direction, and then we have our data that includes both nuisance and experimental design. If they're perpendicular to each other, then we can just figure out how much of the data is explained by the experimental design by just projecting down that vector to the experimental design space. It's only got 1 dimension in the space, but that's a good enough space. That's still a space. And so that's what the P matrices are. So the P matrix is basically something that projects a vector down to the X space. So this guy's a matrix, and you multiply that by a vector, and what is the result? It rotates the vector and shrinks it a little bit so that it corresponds to the perpendicular projection of that data vector onto the experimental design. So that's the meaning of this matrix. It's a matrix that will do this operation for you of projecting onto the x-axis. But the problem we have is that the nuisance variables are not perpendicular to the experimental design, and that's always the case. And so now the problem is, and then we've got some data somewhere in there. So here's our data, and so what we really want to do is kind of do an oblique projection. So what we want to do is just project down to the experimental design matrix direction, but do the projection parallel to the nuisance, so that we don't get confused about who gets to actually explain things. So that's actually, if you read in the Tom Liu paper, you can visualize that as a matrix that will operate on a vector. So that guy is basically our oblique projection. So this guy says project parallel to the S down to the X direction, and then figure out what that vector is. So this guy will do that. This guy will do that. So that's the problem we have to deal with, is this oblique projection problem. Okay, so back to where we were. So we've got this space of everything in it. It's got both the experimental design as well as the nuisance factors. And so let's start here, and we'll draw a direction in here, and this guy is our, make it a little longer. So this is our unit S. So that's we only have one dimension. So if we set the length to 1, what direction does it go in our experimental design plus nuisance space? And then we also have another direction, which is not necessarily parallel to that guy. And so this is our our unit x. So this is our unit nuisance direction and our unit x direction. In real life, there's many dimensions to this, but here we've just got it. Here we just have it with 2 dimensions, only 2 dimensions. Okay, so now we've got the data, and so the data. So here's the data. So the data, remember, doesn't have to be in. The data is not. Nobody said the data had to be in the space of things that can be explained by the experimental design and the things that can be explained by the nuisance. It could just be anything. The data is free to do whatever it wants. And so here's the. So this guy is the data. Data. So that's the y vector. So this guy was the. Gotta get my colors right. So that's the. This is the unit vector. Unit x. This guy is unit s. Unit s. Okay, so now we can do some projections, and so what's the first one? So one thing we could do is we could just project the data onto the unit vector, just perpendicularly project it onto the nuisance variables. So that would be sort of coming down sort of like this. And so this is supposed to be a right angle onto that guy. So what is that? So that's data. This is data projected onto nuisance. But then we also might want to know like how the data projects onto both of these guys. And so where's that vector? That's yet another vector. So we're going to have to introduce 2 more. So this guy is the oblique projection onto nuisance. So this guy is E x of the y vector. So that's oblique project onto nuisance. And then we have the same thing for this guy, which is oblique. Did I put that? Oh yeah, sorry, that's an S, right? So here's EX. So this is oblique project onto experimental design. That's this guy. And then we could add those 2 together. So if we add these 2 together, we're going to get something over here like that. And so that vector is basically the orthogonal projection of this guy. So this is supposed to be a right angle there. So that's so that vector is the orthogonal right angle orthogonal projection data onto XS. So that's how much of the data that the nuisance plus the experimental design can explain. We're almost done. And so then there's one last vector, which is this guy right here, which is the one we really want. So this guy is perpendicular over here. So what is that guy? Data projection. Let me just move this guy down a little bit because I didn't explain last ones. Okay, so that guy's up there. This guy is going up there too. They're all going to the same place. And the data projector into the nuisance was that guy. I didn't define this. There's two vectors to define here. Those are the two most important ones. So let's start with this one, which I drew, but I didn't define. So this guy was the vector. You project the data onto both the experimental design and the nuisance at right angles. And then what is the vector that describes how far you are up to the data? That's the error. So this guy is basically this is the error. You know, that's the part of the data we couldn't explain. And so that error error not explained by experimental design plus nuisance. And so what is that? That's actually this guy down here. So let's see why this thing actually corresponds to the error. So if you look, if we look at that equation, the equation has an I, minus the projection matrix that rotates the data vector down here, figures out how much of it, what's the length of it, after you perpendicularly project that data down into this space, and then times y. So why does that sort of equal this? Why does that equal this thing? Well, so what this says is basically identity times y is y minus the projected down into this plane times y. And so what is that? That just means like this vector minus this vector. And what is that? Then it's the vector that is the difference between those two tips. So that's the error. And so this guy is basically the denominator. It's got another y in it to square it, but we'll just ignore that for now. So this guy's the denominator of our F ratio, signal to noise. And then finally the last one, the numerator. And so the numerator here is, so how much, so this is something that's perpendicular to the nuisance function so that we effectively do this oblique projection. So how much more of data can we explain? By adding experimental design. Now, if we just said how much of data we can explain just with experimental design, that's this guy. So we could do something. We could draw one last one in there. I'll just dash it. So what we could do is we could just project this guy, directly down to here, to the experimental design matrix, and ignore the ignore the nuisance one. So that guy would be, you know, the projection. So this is, you know, so this vector here is the, you know, orthogonal projection onto experimental design. But that doesn't take into consideration that the nuisance vectors are not uncorrelated with it. And so we've got this problem of sort of crosstalk between the nuisance vectors and the experimental design vectors. And so the way we fix that is we say, we're only going to look at the difference that's perpendicular, uncorrelated with the nuisance vectors. And that's what this number is. So how much more of the data can we explain by adding the experimental design? So, and so this guy is the numerator. And why is that the numerator? So that's, you know, the equation is the projection onto the combination of the experimental design and the nuisance of, so, the equation is this, you know, minus just the projection onto the nuisance, like that. So we just distribute this. So we project this guy onto the combination. That's this vector here, and then we subtract off projecting this guy just onto the nuisance, and that would be, I didn't draw the vector, that would be this guy, just onto the nuisance. And when we subtract those guys, then we get this resultant vector that's perpendicular to the nuisance. And so that's our proper numerator that takes into consideration that there's some correlation between the experimental design and the nuisance. So that's the final insult. So that's the full picture of, you know, how you can deal with these partial correlations that you have to take into consideration, because it's virtually impossible to make any kind of experimental design that isn't partly correlated with the various nuisance variables that can occur. So especially when you consider, like, what are our nuisance variables? So our experimental design is something, you know, something like this. And our nuisance could be like that, or it could be something like that, or it could be something like that. So all those things you can easily see, you know, say your random experimental design has just a few more ons of this particular condition type over here. Well, then it's going to be partly correlated with this guy. So that's the bottom line. So now one last thing. This kind of way of thinking about or solving this problem, you might have heard that there's kind of a difference between event-related design and a block design. You might have thought of those two things as somewhat different from each other, but in fact, they're not different from each other. This kind of way of thinking about it applies. This deconvolution method of thinking about it applies to block design as well as event-related design. And so, you know, so our GLM, you know, it's okay for block design. That's kind of the way I've been illustrating it. But it's also fine for, you know, so-called event-related design. They're not different. And they're not different in the way that they're the way that they're analyzed. And so I didn't say what is an event-related design. A block design is basically an event-related design, but where you've got long blocks of particular events of the same kind. So in a block design, you'll do something like turn on condition A for 15 seconds. And so what you can view that as I turned on condition A, and then I kept it on, and I kept it on, and so each one of these things are separately generating an hemodynamic response function, and then we turned it off. And so what does that generate? Well, when you first turn it on, the hemodynamic response function will come up, and then eventually, after sort of being hit multiple times by this same event, we'll sort of like reach sort of more or less a plateau, and then we'll fall off like that. So you can view a block as just a bunch of small events. That's actually mathematically the way this works. You're just doing a convolution, and the thing you're convolving with, it just had a whole bunch of small events of the same kind following each other. So what's an event-related design? Event-related design is instead do a bunch of short events, like a couple seconds or 1 second. So we do one event like this, and then another event of the same kind, and then maybe we'll mix in event type 2, and then back to type 1, and then maybe back to type 2 a little bit later, and then maybe 1 again, etc. So what happens in this case is that when you look at, so this is the response. So what happens in this case when you look at the response is this guy is going to sort of generate a hemodynamic response function, but long before it's died away, there's going to be another one on top, and then here's a different condition that's going to generate a different hemodynamic response function, and then that'll decay away a little bit, and then there's another one, and then here we got a chance to decay away a little bit further, and another one, and another one. It's actually the same thing as this. It's just that the events are all sort of randomized in time. And what is the point of this? Well, if you read in the Tom Liu paper discusses this in some detail. So if you read in there, what you'll see is this is better for just detecting whether detecting a response. So this is better for detecting a response. It's worse for trying to estimating shape of the hemodynamic response function. And the reason you can see why it's not very good for trying to estimate what this particular shape is, because basically the only place where we can actually see the shape of that is basically when you turn it off or when you turn it on. But the problem is we don't have very many samples. We immediately start slamming a bunch of other stimuli on, and so we can't actually easily measure the shape of the hemodynamic response function. So this kind of method is much better for measuring the shape of the hemodynamic response function because our stimuli are spaced at all different lengths, and so we have all different amounts of overlap of the hemodynamic response functions, and that gives us more ability to actually pick out the shape. And so the event-related method is better for detecting. So this is just better for just detecting whether the response was there or not. This is better for detecting the shape of HDR, but it's actually worse. So it's better for detecting, but it's actually worse for detecting whether something occurred. Worse for detecting occurrence. And why is that? Well, let's just imagine what our data actually looks like. So, I've drawn it out here as like a perfectly smooth thing like that, but that's not actually what the data looks like. What does the data look like? Well, here's the data. You're not doing anything. This is the off condition. Your heart is beating, you're breathing, and then you do one of these events. So here's an event. And so what happens? Well, maybe it goes up a little bit. And then that's pretty much, that's pretty much it. So that's your whole response. And you can see like this little breath that came before your response was, about the same size, barely detectable. So you have to do a whole bunch of these in order to rise out of the noise. Now let's compare that with a block design. So with a block design, here you're breathing and your heart's beating. And then the block design comes on and you start to go up a little bit, but then, after a while, you got like a reasonably good response going before you turn it off. And so the difference between this is actually kind of visible, whereas the difference between, sort of the average of that and this thing is, can be quite small. It's just a very small difference. And so this is better. So in general, you want to do a block design if you have a small signal and you're just trying to detect whether something occurred. In the case of if you are, on the other hand, interested in the actual shape of the hemodynamic response function, like does the hemodynamic response function, go up quickly, or does it, versus it's kind of a very slow, leisurely thing. If you're interested in that, then you generally want a block, an event-related, a so-called, event-related. But, in some respects, these are basically the same thing. Now, there's another reason why you might want event-related, which is maybe you just can't do whatever you want to do a whole bunch of times in a row. It doesn't make any sense. It might be hard to sort of glom your experimental design events together into 15 seconds of stuff. And so that's not the only reason to do. You might be forced, in some respects, into an event-related design in order to just be able to do your experiment at all. But keep in mind, if there's some way that you can actually turn it into a block design, you'll be more efficient at detecting whether a signal has occurred. So that's the kind of higher level conclusions that you can draw after doing all the math of trying to sort of figure out how these things work. And so if you read in the Tom Liu paper, you can see arguments exactly on this topic of why doing a block design is actually better for just raw detection of whether or not a response has occurred, independent of the hemodynamic response function. Okay, I think I'll quit there. I think that was a full house, so we'll stop recording there for now.